The expression ax equals b modulo m is called a linear congruence. And well, if this was a linear equation in the general sense, not under modular arithmetic, but usual arithmetic, this would be quite an easy equation. On the other hand, when it's a linear congruence, it's a little bit more complicated because we don't define division directly in modular arithmetic. It's defined via multiplicative inverse. So using solving linear congruences requires using multiplicative inverses. And the solution in general to such a linear congruence is x equals inverse of a times b modulo m, where if it exists, this is the multiplicative inverse of a modulo m. As we have stated earlier, this doesn't exist always, okay? And when it doesn't exist, there doesn't exist a solution. And another important point to point out in general, for instance, if you have an equation 2x equals 8, you can cancel out common factors in both sides to write x equals 4 in our usual arithmetic. But that is not the case when it comes to modular arithmetic, and we cannot divide both sides of a congruous relation by the same number. For instance, 14 and 8 are congruent modulo 6, but if you, let's say, divide both sides by 2, you get 7 on the left-hand side, you get 4 on the right-hand side, and clearly they are not congruent modulo 6. Okay, so you will have to be careful about canceling, let's say, both sides of a linear congruous relation under modular arithmetic. So it looks like you need to compute at each case the multiplicative inverse, if it exists, of the coefficient a. Now, at this point, here we are going to see under which condition you can actually do this simplification from, let's say, 2x equals 8 to x equals 4. We have seen that you cannot do this in general in modular arithmetic, but there are cases where you can do this, and we will see when that is the case. First, let's look at this lemma. If a, b, c are positive integers such that a and b are co-prime, you see GCD of a and b is 1, means they are co-prime, then if a is if a divides the product of b and c, and then a must divide c. Now this looks like a trivial result. Obviously, if a and b are relatively prime, which means a doesn't divide b, but a divides b and c, then a must divide c, right? Let's show this. And here you see the application of Bezout's identity. Since the GCD of a and b is equal to 1, then there must exist s and t integers such that the GCD 1 equals as plus bt, which means if you multiply both sides by c, you get c equals a times s times c plus b times t times c. Okay, now when you look at c, the expression here, clearly this is a multiple of a. Okay, and we know that since this is given to us, a divides the product of b times c, a is also a factor of b times t times c, because it's a factor of b times c. Therefore, when you multiply it with an integer t, a is still going to be a factor of btc. So a is a factor of this term, a is also a factor of this term. Therefore, when you add them up, clearly a should be a factor of the sum, which is c. Therefore, a is a factor of c. Now, based on this lemma, we have this theorem for integers a, b, c, and positive integer m. If the product a times c and b times c are congruent modulo m, Now, recall we said that in the general case, you cannot factor out these C's. You cannot write A congruent B modulo M in general, okay? That was our case. But if C and M, the common factor in both sides, and the modulo, if they are co-prime, right? If their GCD is 1, then it's possible to factor the C out. And you can write A congruent to B modulo M in this case. Here is the proof. It's quite simple. A times C is congruent to B times C modulo M. This means M divides AC minus BC, which is equal to C times A minus B. Now I have M divides C times A minus B, but I know that C and M are relatively prime, okay? This means I can apply the lemma. I know that M is a factor of C times A minus B, but M and C are relatively prime, which means M should be a factor of A minus B, which means A is, by definition, congruent to B modulo M. So this means if you have such a congruence relation, in general, you cannot cancel out the common term C, but you can do that only if C is co-prime to the modulo value M. Okay, let's continue with this theorem. If A and M are co-prime, where M is greater than 1, then the multiplicative inverse of A exists, and it is unique. Here I'm going to show just the existence. Uniqueness part is not that difficult. Again, the proof is by Bezout's identity, and since the GCD of A and M are since they are co-prime, this GCD is 1, then there exist integers S and T, the Bezout coefficients, such that 1 equals S times A plus T times M, okay? T times M obviously is divisible by M, so it's congruent to 0 modulo M, and therefore we have, since this is congruent to 0 modulo M, we simply have S times A is congruent to 1 modulo M. So by definition, S here is the multiplicative inverse of A. Okay? So for instance, a very easy example here, solve 3x congruent to 4 modulo 7. To solve this, you need the multiplicative inverse of 3. And the multiplicative inverse of 3 modulo 7 is 5, because 3 times 5 you get 15, which is congruent to 1 modulo 7. Therefore, by definition, 5 is the multiplicative inverse of 3 modulo 7. And therefore, the solution is multiplicative inverse of 3 times 4 modulo 7, which turns out to be 6. If you plug it in, 3 times 6, 18. That is clearly congruent to 4 modulo 7. Now, here, we sort of observed that 3 times 5 is congruent to 1 modulo 7. So how to find the multiplicative inverse of a number under some modulo arithmetic? You cannot really try everything out. But you see, the multiplicative inverse of A modulo M can be computed via Bezout identity, because we have seen in this proof that actually one of the Bezout coefficients is the multiplicative inverse of A. Therefore, since we have the extended Euclidean algorithm that gives us Bezout coefficients, you do not really need to try out every possible value in the set Z sub M, because you see, if M is large, if the modulo value is large, for instance, I mean, it could be any large value, even if in the order of hundreds, if you are solving this on pen and paper, it would be quite tedious to find the multiplicative inverse. But if you apply the extended Euclidean algorithm, That will give you the pair of Bezier coefficients, and you can quite simply find the multiplicative inverse of the coefficient here. Now, an important observation here is if P is a prime number, and that is the modulo base, let's say, it will be co-prime to any A in this set, Z sub P, obviously, which means all elements in this set, Z sub P minus 0, because 0 never has a multiplicative inverse. But since the modulo value is itself a prime number, it will always be co-prime to any coefficient you have, right? Therefore, if your modulo base is prime, then the elements, all elements in your set, except 0, are guaranteed to have multiplicative inverses. This means that if P is prime, this structure, as we have seen earlier when we studied group theory, is actually a commutative ring because it satisfies all the axioms or in the definition of a commutative ring. In addition to, well, obviously it has now multiplicative inverses. This is quite an important ring. It's sometimes denoted using this notation. And this also means that the structure, the set Z sub P, along with addition and multiplication, is a field when the number P is prime.